Now, if you've been following the presentations in order here on pilottraining.ca, you've already seen and learned that when it comes to weather, it all starts with the sun. The sun sends warmth towards the earth, and then as that warmth strikes the earth, it's going to hit various surfaces: land, ocean. What this is going to then do is that air sitting over top of the earth is going to start to take on the properties of what it's over top of. And this, when a big parcel of air sits in a certain place on the earth and it starts to take on the properties of the earth below it, this leads to the development of what we know as the air mass. In this section, we're going to take a close look at the air mass, and we're going to see how, once air masses start to interact, it causes weather. Now, air masses on their own, of course, can also create and cause weather, and we'll take a look at that. But things get really interesting when air masses start to collide. But we'll come back to that part of the story towards the end of the presentation. For now, let's study air masses. Let's study what happens when a big parcel of air sits for an extended period of time on the surface of the earth. So, when it comes to air masses, here's the definition. An air mass is a large body of air, usually 1,000 miles or more across, that has similar properties in terms of temperature and moisture in the horizontal. Now, those two key items determine what an air mass is ultimately: temperature and moisture. This means that when we take a horizontal slice of an air mass, at any given height, the properties of that mass will be uniform. So we have the surface of the earth, and if that air mass happens to be cold and dry, if we moved from one end of, say, maybe Western Canada to the other end of Western Canada, we would find that the temperature and humidity of that air mass are the same. If we then moved above the surface of the earth in that same air mass, we would again find that temperature and humidity at that particular height are constant and consistent. Now, when it comes to actually developing an air mass, it's kind of best that they sit around and really do not much or move very slowly. So, of course, the best source regions for air masses are going to be large, flat areas. This will allow that air to sit there long enough to take on the characteristics of the surface below it. What this also means is that a high pressure area is going to be the best sort of area to create an air mass. Remember, if you have that air that is slowly kind of sinking a little bit and spreading out slowly across a large air or region, you're going to have the best chances of developing an air mass. When it comes to air masses, because we have a constant temperature, that means that the winds are also going to vary very little throughout an air mass typically. There's not going to be a huge pressure difference, so the winds can't really get going because we need large differences in pressure, and temperature helps drive those differences in pressure. So when it comes to air masses, we've talked about source regions. The region in which an air mass forms is known as the source region. And, as we've seen, an air mass will take on the properties of the area in which it is formed. That's simply because it sits there for so long over a period of time. So, let's think of maybe an air mass that forms in the high Arctic. If it sits there for long enough, it's going to get good and cold. Of course, if it's over land, well, in this case, it's going to be dry. There's not going to be as much moisture, say, as if it formed over a large body of water like an ocean. One, of course, that formed over the Gulf of Mexico down to the south, well, it's over a body of water, so it's going to be moist. And then in terms of temperature, of course, it's pretty warm down there in Texas and Florida, so we're going to have a warm and moist air mass. So here's a little bit of a global picture of air masses, and when it comes to Canada, they're common regions of formation. We can see that as we look at these air masses, you can see that they have identifiers. CA, MA, MP, MD. We'll start to go over those in a little bit more detail. However, what I want you to notice for now is let's look first off at this continental Arctic here. The C stands for continental, the A stands for Arctic. So what this tells me is that we actually had, you can see continental Arctic, there's the source region. It's forming over largely very big, vast areas of land or frozen ice. So that's going to make it dry. And that's why we have the designator of continental. Formed over land, it's typically going to be dry. For Arctic, of course, well, it formed in the high Arctic where it's cold, so that gives us our temperature designation. Next up, let's look over here. You can see that this one is called Maritime Arctic, MA. So it formed up here over the sea, so it's going to be moist. When we look at the A, again, that's Arctic, so that means that it formed where it was cold. So this one's going to be cold and damp. Of course, air masses don't just always sit there. They do tend to move around a little bit. And we'll talk about how motion of an air mass can actually modify it from one type to another. One example is seen down here, where you can see the source region for this. Well, it's over the ocean. It's very damp, so moist. It's going to be maritime. And it's in the far south. It's right near the equator. So we're going to call that tropical because it's very warm. As this moves, though, you can see eventually it encounters North America. So as it moves across this dry land, it is possible as it slowly moves for it to start to modify itself. And we can see here where we now have continental tropical. Not a very common type of an air mass, but it is possible. So moving on. As we've discussed, the source region of an air mass will always occur in an area of high pressure. Slow-moving highs are the best areas for forming air masses. And this is simply because in order to establish the uniformity of temperature and humidity, the air needs to sit there or be very slow-moving for an extended period of time. A week or two over a uniform area of the Earth's surface will generally do the trick in terms of creating an air mass. Now, even though the moisture content and the temperature of an air mass are uniform, this doesn't mean that they are devoid of weather. Weather can still and will happen within an air mass. If we have a large area of air, and if we have that air mass, the weather will be determined by each of these following factors. The moisture content. Of course, the more moist an air mass is, the more likely it is to develop some sort of weather. We also have the stability of the air mass. A stable air mass is less likely to produce any sort of weather, and if it does, it will be different than an unstable air mass. This one becomes the biggest one of the bunch, though, however. If we happen to have a cooling or a heating process present in conjunction with this or this, that can definitely determine what type of weather will end up happening within an air mass. Now, as you move towards writing your exam, we want you to be careful because the types of weather that we can get in an air mass are different than the properties of an air mass. Okay, so Be very cautious with that difference here. The weather in an air mass is determined by these three factors. However, when it comes to the properties of an air mass, remember that's uniform temperature and humidity throughout that big parcel of air. So moving into more detail on classifying air masses. Since the type or types of air masses have a big effect on the weather, it is helpful to give them names. Now remember, we can have weather within an air mass. However, as we get towards the end of this presentation, you're going to see that when types of air masses collide, we get what are known as fronts, and that really gets the weather going. So going back to the air mass, however, when it comes to the name of an air mass, it's dependent on the temperature and humidity of the air mass. You saw that when I pointed that out to you in the slides earlier. Continental Arctic, continental polar, maritime tropical. These, of course, were determined by their source regions. So the name, temperature and humidity, well, I should go around. It's actually humidity and temperature. And then that gives the air mass its name because of the source region from which it started. Now, remember, within an air mass, you're going to tend to have similar weather. It's a uniform parcel of air, right? It's useful to name and classify these masses of air because it can tell us a lot about what weather can happen within them. Remember, the first part of the name, as you have seen, is going to be the moisture content. The second part is going to identify the temperature of that particular parcel of air. So here we have the two main moisture determinants. We have continental, which as I've described to you is dry, and then we have maritime, which as I've described to you is moist. When it comes to temperature, well, we have three major types of temperature. We have Arctic. These tend to form in the high north, and these are cold parcels of air. We then also have polar, which is kind of halfway between the Arctic regions in the far north and, of course, the more equatorial regions to the south. So in Canada, surprisingly, polar air masses aren't very common. These, however, of course, aren't freezing cold, but they're cool, cold air masses. Finally, to the far south, we have tropical air masses. And these, of course, are going to be very warm air masses. So very simply, if you just think of the Earth in terms of high north is Arctic, and then kind of in the middle areas, we have the polar region, and then further down, we have the tropical region. And these actually kind of tie in a little bit with the three cells of circulation that we have when it comes to global circulation. And maybe you looked at that earlier, again, in pilottraining.ca as well. So when we look at these various determinants and we put them all together, we can see that there's 6 main types of air masses that we can end up with. We can end up with, and again, this is moving from north to south, we can end up with continental Arctic. We can also end up with maritime Arctic. We can have continental polar, but then of course we can also have maritime polar. And then finally, we can have these two, the continental tropical and the maritime tropical. So when you're thinking of air masses from northern regions of Canada to the southern regions of Canada, this would be how you would go about listing them and naming them. CA, MA, CP, MP, CT, MT. Now, interestingly enough, when we look at air masses within Canada, it's pretty rare that we actually end up with, say, continental polar. Now, just jump back to the map here for just a moment, just so that you can see all of these various air masses that we've just talked about. And you can see their large regions, their source regions. And then you can also see the typical motions that they will make when they start to move a little bit. In Canada, I know just a few moments ago we listed 6 air masses. However, in Canada, there are really only 4 main types of air masses: continental polar, and, as I pointed out earlier, continental tropical air masses are very rare. So, in Canada, going from north to south, make sure you know these. The most common air masses moving from north to south are continental Arctic, predominantly a winter type of an air mass. We also have maritime Arctic, or MA. These we usually find in Canada in the summer and winter. We also have maritime polar, MP. These tend to be formed in the summer and winter as well. And then finally, we have maritime tropical, which is primarily a summertime air mass in Canada. Not always, sometimes they can creep up during the wintertime as well. However, remember for the exam, CA, MA, MP, MT. Most common 4 air masses going in order from towards the pole towards the equator. So let's look at each of these air masses in a little bit more detail individually. First off, we have the continental Arctic. Remember, cold and dry. These originate north of the Arctic Circle. Of course, temperatures, and here's where it's confusing sometimes, because we just said temperatures in the polar regions, but we said there's also polar air masses, but the air masses that form in the high north are actually called Arctic air masses. Temperatures in the polar regions allow the air to cool to an often bone-chilling and record-breaking low temperatures. It sits there over the cold frozen ice for an extended period of time, and of course it becomes very dry and very cold. Now, we've all heard about the polar vortex, right? Well, when these continental Arctic air masses plunge southward in the winter, they create these polar vortexes, as we sometimes call them, in big fancy names to get, everybody all excited about them. But cold air moving southward is going to be continental Arctic air. These aren't as common during the summer, however. And that's because, as we mentioned at the beginning of this presentation, the sun helps drive these air masses, right? So in the summertime, we've got pretty much 24/7 sunlight. So as a result, there's a little bit more warmth up in the northern areas. So it's not as common that we're going to have one of these form and come plunging to the south in Canada. The next common air mass in Canada is the maritime Arctic. These, of course, are cold and moist. These air masses usually form a little bit further to the south of those continental air masses. And when it comes to Canadian weather, these actually are one of the most dominant ones, particularly during the winter and particularly along coastal areas. During the summertime, if we get one of these, in the more middle areas of Canada, the interior of Canada, they will frequently bring convection and showers. Now, here's something surprising. During the summer, maritime Arctic air can form over the Canadian North in locations that are actually far away from the ocean. I mean, when you look at the photos of the air masses that we looked at earlier, well, normally maritime formed over big open seas, right? In the summertime, however, a lot of people forget that Canada has a lot of lakes in the far north. So it is possible that we could actually have maritime Arctic form over the high northern areas of Canada in the summertime. All those lakes would put in a lot of moisture into the air, and we'll end up with a maritime Arctic air mass that actually developed over land, kind of head scratcher initially until you look at a map of Canada and see how many lakes there are in northern Canada. So, this is a common exam question, probably because most people don't think of maritime Arctic as having the possibility of forming over land. Now, when it comes to maritime Arctic, these air masses tend to be less stable as well. Lots of moisture, okay, so that's going to help drive some instability. Now, maritime polar. If we encounter these, they are cool and moist. These typically form over the northern Atlantic and the northern Pacific Oceans. They usually bring cloudy and damp weather to Canada. They most often influence the Pacific Northwest and the Atlantic Northeast. Maritime polar air masses can form any time of the year, and they are usually not as cold as the continental polar air masses. As for maritime tropical, well, these are warm temperatures, lots of moisture embedded within these, and because it's warm air, remember, it has the capacity to hold even more moisture than cold air does. So these are very, very wet air masses. Maritime tropical air masses are the most common across eastern Canada. They typically originate over the warm waters of the southern Atlantic Ocean and the Gulf of Mexico. These air masses can form year-round, but they are most prevalent across Canada, of course, throughout the summer months. When it comes to those hot, humid, muggy days of summer that you experience, those are typically the result of a maritime tropical air mass that has moved up into Canada. And then we're usually in for a sweltering heat dome. So, as we've been talking about, an air mass sits there and it kind of forms, but at some point, sometimes they like to start to move. How and why they start to move is a little bit beyond the scope of this presentation. Just know that they do start to move. And if they do start to move, well, it's possible from them to become modified. And they will start to take on the characteristics of the area that they are passing over. I know that I introduced to you the maritime tropical here, moving across the continental land area of North America and becoming continental tropical. Not commonly does that happen. Maritime tropical is typically very powerful and doesn't let these masses move in too efficiently, but it's possible for them to become modified. And if they do, you need to know how these modifications can change the weather within that particular air mass. Very important to know and understand as a pilot and to know for the exams. So here's a few examples of what could happen. Let's say that in the high north we have some continental Arctic. So here's that big parcel of continental Arctic air. It starts to slide maybe, say, southwards, and maybe it eventually bumps into an area where we have lots of, say, moisture and warmth. So as a cold air mass moves over a warmer surface, of course, this is going to start to pick up some moisture and the temperature of the air mass can become warmed. The lower levels, in particular, moving over this warm water, so the lowest part of this air mass are going to become warm and moist, and that's going to lead to what we call a more unstable air mass. Remember, this is cold, so now the whole thing moves over this warm, moist air, so the bottom layers of this air mass start to become warm and moist, while the overlying colder air allows that warm air to move upwards. So now we have some convection starting to happen. And we can end up with, an unstable air mass with lots of, say, showers occurring within it. Now, what if a warm air mass, maritime tropical, is warm and moist, this parcel of air, and now it starts to move into, say, a continental area where we've got, say, cold land and very dry conditions. In this case, what will happen is the lower layers of this air mass are going to get cooled. So that's going to tend to have a stabilizing effect on an air mass. Remember these for the exam because it's a common question. What will happen if an air mass becomes modified? And they'll give you an example of it moving over a specific new source region. So, as we've seen, the modification of an air mass can sometimes be great enough to create a brand new type of an air mass. The extent to how much an air mass is modified depends on the speed at which the air mass is moving, the moisture content of the area over which it is passing, and the temperature difference between the air mass and the new region. Generally speaking, the greater the difference is here, the more the modification will be. So if we have an air mass that is stable, we would have an air mass with poor low-level visibility. Typically, we're going to have layer-type cloud. The precipitation will be more steady. We will have steady winds that can change quite a bit with height, and we're going to have smoother flying conditions. If, however, we have an unstable air mass, believe it or not, unstable air masses result in good visibility. And that's because there's going to be a little bit more up and down mixing, that convection that we discussed earlier. You're also going to end up with convection-type cloud. The precipitation will be more showery. If we do have those winds, they're going to be gusty, and there might be some very bumpy characteristics associated with this air mass. So let's now start to discuss in a little more detail modification, advanced modification topics when it comes to air masses. Remember, as an air mass moves from the source region to a new region, just like I showed you in that slide about 2 or 3 slides ago, big parcel of air moving over a newer area, you need to notice and remember that it will be modified either through cooling from below or through warming from below. Remember, the air mass is going to move over a new source region, so it's going to be the bottom of that air mass that is most affected, and it can either cool or it can warm. All right, so when it comes to warming from below, what will happen? This warming can happen by solar radiation, or it can happen by passing over a warm surface. Remember, we're now going to have slightly warmer air at the bottom of the air mass and slightly colder air at the top of the air mass. Well, warmer air likes to rise, right? So instability and convection will result if we move over a warmer area. This convection and instability will mix into the higher levels of the atmosphere, and it can lead to modification at considerable heights. If the lapse rate of an air mass was steep enough, this instability could extend to the tropopause. Remember this: an air mass that is modified by warmth from below becomes more unstable. Warm air at the bottom, cold air at the top. Nature doesn't really like it that way, so as a result, we're going to end up with that warm air rising and trying to go upwards. Now, this is a little bit more advanced. For the rec pilots out there, I don't think that we're going to see this too much, but weather charts might sometimes have a K or a W tacked on to the end of the name. So as an example here, we have continental Arctic, but then it has K at the bottom. So if we see this, what that's telling us is that the air mass on top is colder than the surface below it. I often like to think, well, K, C, colder, colder, K, K, K. Okay, yeah, sure, we can go with a K then for colder. So this means it's a cold air mass over top of a warm surface area. Whenever we see that third designator, we know that it's an air mass that has been moving and is being modified. Now, look at this one here. CT, continental tropical, warm. So what this means is we have a air mass that has been moving, is being modified, and it is warmer than the surface that it is sitting over top. That one's pretty easy. W. W for warm. K for cold. Yeah, okay. So, if an air mass is modified by cooling from below, such as by passing over a cold surface, then we have an inversion. Colder temperatures below, warmer temperatures above. The warm air can't rise now because there isn't any warm air down there. Air that tries to rise is going to find warmer air above it, so it's just going to say, I can't do anything. So as a result, inversions resist mixing, and they lead to modification only in the lowest levels of the air mass. An air mass that is modified by cooling from below will tend to become more stable. Again, know this for the exam. Weather charts, as we've just seen, will depict such an air mass that's being modified by a W at the end, just like this CTW that we've got here. So we now are going to start to move into a very brief introduction to what we call frontal boundaries. If we have two air masses and they suddenly collide, well, we're now going to have areas where the air is maybe fairly warm versus areas where the air is fairly cold. Maybe it's very moist on one side, very dry on the other side. So where these air masses collide, those areas are known as fronts. And when it comes to fronts, we'll talk a lot more about fronts in the section called Fronts and Frontal Weather. You can see a very simplified diagram here of where we've got that continental Arctic front, so right here, so we've got cold, dry air. Meanwhile, we've had maritime Arctic air that's moved in through here, so we've now got MA, so moist and cold air. And then in here, well, maritime polar, and then finally down here, maritime tropical. So again, this tends to be the most common air masses in Canada, moving from north to south. Continental Arctic, maritime polar, and maritime tropical. So sometimes you can think of them, and remember, they're moving around, but sometimes you can think of them in this idealized picture here as literal layers across Canada from north to south in terms of the uniform humidity and temperature properties. Okay, now this here, notice that it says CPL exam, so I think that you can safely ignore that, but this part here you're going to need to know that we've just talked about which air masses from north to south occur in Canada. There you go. Now, when it comes to air masses and their heights and their temperatures, it is good to know a little bit about this. First off, when it comes to air masses, an air mass is always topped out at the troposphere. Remember, it's going to go from the surface of the Earth, so down here, but then that air mass is going to exist up through the atmosphere. And that air mass is going to be topped at the troposphere. Here's an interesting thing. The warmer an air mass is, the higher it will cause the level of the tropopause to be. So a warm air mass, you're typically going to find that it's going to end at a much higher altitude than, say, an air mass that is a colder temperature. Here's something that's a little bit weird. What this also means is that the tropopause, at the tropopause, the temperature of the warmest air masses, such as a maritime tropical or maritime polar, will actually be a lot colder than an air mass that is cooler, such as the maritime Arctic or continental Arctic air masses. Now, initially, this seems to defy logic, but the temperature versus height diagram in the next slide will show this, as well as a glance at the constant pressure charts. Now, as recreational pilots, you're not going to get a constant pressure chart, so you can look at it with just, okay, that's nice to know and interesting to know. However, this bit here, with the temperature being colder with a warm air mass at the tropopause, is a question that, believe it or not, you're still possibly going to get on your recreational exam. So here's how we would look at this. If we look at air masses from the side, here's the northern parts of Canada, and then here is the southern parts of Canada. Remember, we have continental Arctic, maritime polar, and then maritime tropical. Remember, the warmer one of these air masses are, well, of course, those molecules are moving apart a little bit faster, so that's going to cause the air mass to spread out. The easiest way for an air mass to spread out, actually, though, is for it actually to move upwards. So this cold continental Arctic air, when we look at the top of it and the tropopause height, you can see that it's fairly low. If we move here to the maritime tropical, because of that expansion due to all of the warmth, you can see that the tropopause is a lot higher. Now, what this means is that when you think of the standard atmosphere and how we say that it typically cools at about 2 degrees per 1,000 feet, well, if you look at the depth of continental Arctic air, even though this might start out colder on the surface, let's say this is -20, and then maybe this one here is like +20, even though this is colder on the surface, it has less depth for that lapse rate to take effect. So as a result, the temperature at the top of continental Arctic is actually going to be a warmer temperature than the maritime tropical temperatures. There's a lot of depth here for 2 degrees Celsius per thousands. There's a lot more thousands in here than there is here, so 2 times multiple thousands is going to result in a much colder tropopause temperature than right here. So this here sort of shows us this. We have the temperature here, we have each of the various types of air masses, and as you can see, the maritime tropical, look at right here how it has the coldest temperature at the tropopause height. Meanwhile, the continental Arctic here, it's much warmer. Even though the initial temperature here, you can see the initial temperature at the surface, much lower than maritime tropical, but by the time we get to the tropopause zone in here, well, the maritime tropical is a lot colder. Now, looking at a constant pressure chart, you can frequently see this as well. In here, we have areas where, if you look, and this is a little bit more, as I said, an advanced discussion, so for the recreational pilot, this is kind of nice to know. But as we look at the heights of the atmosphere, I can see that in here where the cold air is, cold air in here, so we've got cold areas in here, we've got warmer areas in here, a warmer area in here. I can see that the heights here are higher than the heights in here where all of this cold air is. Okay, if you don't know exactly how to read that, that's okay. Just know that that's how it works. So here's another example of that. And again, kind of showing in the far north, where we have pools of cold air through here, and then we have areas of much warmer air in through here, and in through here, and then another pool of cold air moving in through there. The temperatures aloft are going to be much colder in the areas where we have maritime tropical versus continental Arctic. And then this here is just showing you how the temperature drops with height. So you see minus 17 at 6,000 feet, minus 22 at 9,000, 26, minus 26 at 12, and then minus 38 at 18,000 feet. So there we have it, air masses. As I mentioned,